All right, today we're in totes cash mode for section 5.4. We're going to talk a little bit about strong induction from the beautiful confines of my garage in East Asheville. I hope I can get this done in one video, but I might have to split it into two, kind of like I did for section 5.3. We'll see how well my whiteboard is erasing. Next week I'm thinking about going and getting a better whiteboard. I think the problem with this one is it's a little porous, and so it's very difficult to erase once I already write on it. There's a little bit of a glare, but I hope that's going to be okay and still readable. Like I said, we're going to talk about strong induction today. As you know, if you've read the section already, strong induction is actually not stronger than weak induction or ordinary induction. It just seems to be, because you seem to be allowed to assume more in that all-important inductive hypothesis step. So just like weak induction, it's going to have three steps. A base case, you're still going to establish a base case. In the case of strong induction, you might have to prove more than one base case, and we'll see why in the examples. You'll also have an inductive hypothesis, whereas in the previous version of induction, in so-called weak induction or ordinary induction, you're assuming the hypothesis, or you're assuming the claim to be true for a single value of k. In strong induction, what you're doing is you're assuming it's true for all values up to and including some k, which seems like a stronger assumption, but logically speaking, technically in the end, is not. And then finally, you have an inductive step, which is identical in strong induction to the corresponding step in ordinary induction. Namely, having assumed the truth for all values up to and including k, in the inductive step, you prove that it's true for k plus 1. Just like you would for ordinary induction. So again, to recap, you prove a base case, or in some cases, base cases. Then you make an inductive hypothesis, assuming that your claim is true up to and including some k, and then finally prove that it's true for some k plus 1. And as I said, the reason for proving multiple base cases, you might have to prove multiple base cases, has to do with the nature of a statement that's proven by strong induction. And you'll see that in the examples we do together today. So let me just recap one thing. The three steps: base case or cases. Again, you're proving it brute force, just directly for the first cases, just to jumpstart things. 2, you have an inductive hypothesis where you assume P of n, let's say P of k rather, for all k up to some fixed value of n. And then you prove the inductive step. And I did realize I do want to switch these, because we've been pretty consistent about whether we use n or k. So I'm going to go ahead and switch these. You assume P of n is true for all values of n up to some fixed k, and then you prove for P of k plus 1. All right. So that's the basic structure, and I think this is best illustrated by just diving in and doing an example. In fact, the example we're going to do is the all-important fundamental theorem of arithmetic. We've talked about this before. Essentially, it's that every number greater than or equal to 2, every natural number greater than or equal to 2, can be broken up essentially uniquely as a product of primes. And we're going to prove the pivotal step, which we haven't actually proven. If you think back, we haven't actually proven fundamental theorem of arithmetic. We're going to prove the fundamental step of that using strong induction. So the claim we're going to prove that, this is our first example, prove that any n in the naturals such that n is bigger than or equal to 2 is divisible by a prime number p. So you give me any number you want to, any natural number bigger than or equal to 2, and it's guaranteed to be divisible by some prime number p. All right, so you can already see that our claim is going to be about numbers bigger than or equal to 2. So our base case, we'll just start with 2. So our base case, just as in an ordinary inductive proof, our base case, we're going to have the three steps. So we prove this by induction. Base case, let n be equal to 2. Of course, 2 divides 2. 2 is a prime number. 2 divides itself. Since 2 divides 2, the claim is true for n equals 2. And we've established our base case. Now, the inductive hypothesis, we're going to assume that P of K holds, P of N rather, P of N holds for any N less than or equal to K for some fixed K. And then again, just to highlight the difference between this and ordinary induction, or what we have been calling mathematical induction so far, is that in this case, we're assuming it for all n less than or equal to K. We're not just assuming P of K, we're assuming P of N for all n up to and including K, which seems stronger, but you can prove, we're not going to, but you can prove using ordinary induction that strong induction is actually no stronger. It's called strong induction because it seems like we're assuming a lot more, making it stronger, but we're actually not technically. We can get a little extra oomph just by assuming that the claim we want to prove is true for all values up to and including K. So let's go ahead and do that, and we'll see in the inductive step why we need that extra force in this particular case. So the inductive step, we must prove that P of K plus 1 holds. Okay. So having assumed it's true for all values up to and including K, we must show that it's true for K plus 1. So the key here is the fact that there are two possibilities. So one possibility, or what we'll call case 1, if K plus 1 is prime, we're done, because K plus 1 divides itself. This is exactly what happened in our base case for K equals 2. Because 2 is prime and 2 divides itself, it was the prime number we were hoping to find that would divide 2. So if K plus 1 is prime, it's a prime number that divides itself, and therefore we're done. We've found the prime that divides K plus 1, which is what we want. That's what P of K plus 1 means. Otherwise, we're in a second case. If K plus 1 isn't prime. If it's not prime, that means that it must be divisible. It must be divisible by something other than itself and 1. There is a number, let's call it m, some natural number, where m does not equal 1, m does not equal K plus 1, but m divides K plus 1. That's what it means to not be prime. There's some number that divides it other than 1 in itself. Now, if it's not equal to 1, and it's not equal to K plus 1, it must lie in between 1 and K plus 1. And moreover, since it divides K plus 1, what does it mean to divide? It means there's some other number, let's call it J. Thus, K plus 1 has to equal m times J for some J and m strictly between 1 and K plus 1. I hope you can see that down at the bottom of the screen there. There are some numbers m and j. This is what it means for m to divide K plus 1. That there's some number j so that m times j equals K plus 1. But the way that but because of our assumptions on m being between 1 and K plus 1, forces j to be in the same place. J and m are numbers between 1 and K plus 1. And that means they are numbers to which our inductive hypothesis holds. The reason we need strong induction instead of weak induction here is because there's no guarantee that either of these numbers, j or m, is just one step behind k k plus 1 rather. In fact, it's almost never going to be the case, only with very small numbers, namely when k plus 1 is 2 itself. It's never going to be the case that m or j is equal to k. In other words, unlike in previous examples of induction where we could go one step back and apply the inductive hypothesis, in this particular case, we need to go more than one step back using numbers that are smaller than k and be able to say something about them in order to prove our inductive step. So our inductive hypothesis, again, must hold for numbers that are more than one step back from the case we're currently considering. And that's why we need the extra strength in this case, because we've got two numbers here, j and m, that are less than k plus 1, but they're also, in general, going to be less than k, which means we need to be able to say something about numbers further back, thus requiring strong induction. And again, please take my word for it. There is a proof in the textbook that strong induction is actually equivalent to weak induction, and we're still allowed to do it. But that's the key here, needing to know something about numbers that were more than one step back from our previous case. But because we have assumed that we know something about such numbers, we know something about j and m. J and m are numbers less than k plus 1 and therefore less than or equal to k, about which we know p of n holds. What does that mean? That means there's some number, in particular, our inductive hypothesis implies there exists a prime number p such that, and I apologize, I'm trying to do this without erasing, such that p divides m. But one of the things we proved a ways back was in class, before spring break, we proved that divisibility is transitive. If p divides m and m divides k plus 1, transitivity of divisibility means that p divides m, which divides k plus 1, means that p divides k plus 1, which is what we wanted. We wanted to find a prime number that divides k plus 1, which it will because it divides m some factor of k plus 1. So that's the way that strong induction can work. And again, the reason we needed strong induction and not ordinary, or what we've been calling just plain old induction, is because we needed to go more than one step back from k plus 1. It was not enough that we knew it for k, but that we knew it for all n less than or equal to k, because in general, all we know is that this number m is less than k plus 1. We don't know that it's equal to k. If you look back at our previous examples of induction, you'll see that we always went one step back instead of multiple steps back. I'm hoping that this will erase quite easily. We'll see. At least well enough for me to use the board one more time to do one more example together. By the way, I already have a quiz up for this section. So if you look on our Moodle page, you'll see a quiz. Please note that I've made it so that the quizzes for the videos, the quizzes for each section, are not due until the same week as the corresponding problems are due. So for example, the quiz for section 5.2 is due on April 3rd. And the quiz for this section, 5.4, is not due till April 10th. I've also made it so that the videos are posted a week before the problem submissions are due. So for instance, as I just mentioned, the problems for section 5.1, 5.2, and 5.3 are due on the 3rd, which is a week from today, actually. And the problems for sections 5.4, 5.5, 5.6 are not due until the 10th. So we got one more example I want to do just to kind of solidify this idea of strong induction. And this one will involve multiple base cases. So the trick in this one is going to be to go back to multiple base cases. And in the course of the proof, we'll see why. All right. That's not perfect, but it'll do. So let's say that we are given, back in the day when people still mailed things to each other, we have any number of 3-cent and 5-cent postage stamps. Postage stamps were these things that people used to put on envelopes as payment for sending the envelopes through this thing called mail. And what would happen is you would put something in the envelope, a physical piece of paper, and you would seal up the envelope and you'd put it in a mailbox, and a person would come along called a mail carrier, open the mailbox, take out the envelope, and look and see if there was postage stamps on it. And if there were, they would take it and they would send it to the person that you were sending it to. Kind of like Amazon, only clunkier. So let's assume we had any number of 3-cent and 5-cent postage stamps. We want to prove that any amount of postage of 5 cents or more can be made with these stamps in some combination. So for instance, we could make up 13 cents with 1 3-cent stamp and 2 5-cent stamps. We could make up 12 cents with 4 3-cent stamps. So we don't have to use any stamps of one denomination if we don't need to. Let's see if I switch to a different color here. Please let me know by email or somehow if red doesn't show up. I'm getting kind of tired of the blue. I've got some red here. We'll switch to black and blue if the red doesn't show up on the video too well. All right, so we're going to use strong induction. So the proof, which is by strong induction, we'll start out with a base case. But in this case, we're going to prove 3 different base cases. And the reason we'll do that, and will become obvious when we get to the inductive step, we're going to have to step backward into potentially multiple base cases. So the base cases will be to prove, to make up 5 cents, to make up 6 cents, and to make up 7 cents. To make up 5 cents, it's pretty obvious. As before, pause the video and think about each of these before you continue. But to make up 5 cents, it's pretty obvious. You use 1 5-cent stamp. To make up 6 cents is almost as obvious. You use 2 3-cent stamps. And to make up 7, I just now realized in this at this very point in this proof that it is impossible to make up 7 cents. So we're actually not going to be able to do 7 cents. However, how could we do 8 cents? We could do 8 cents using 1 5-cent and 1 3-cent stamp. We could do 9 cents using 3 3-cents. I'm doing something called adjusting on the fly when I'm realizing that I'm being stupid. And we could do 10 cents using 2 5-cent stamps. All right, so it is not possible to do 7 cents if you think about it, all the different combinations that could potentially make up a number as small as 7. We can do 5, 6, 8, 9, 10. So I'm going to prove that we can make any postage 8 cents or more. This is actually, I'm really glad I made this mistake, because what this is showing us, first of all, is that Anyone's possible. It's possible for anyone to make mistakes. It's also showing the principle in mathematics known as prove what you can, and let your theorem follow your proof. You almost never come up with a theorem without having a proof ahead of time. And generally, if you think you have a theorem, you'll have to modify it once you actually sit down and try to prove it. It's the mathematical version of the joke where the guy is looking for his car keys underneath the streetlight. His friend comes along and says, "Did you lose them over here?" No, I lost them over in the bushes over there." "Well, why are you looking here?" "That's because there's a light." You look where there is a light. You prove what you can prove and not something different. So we just modify our theorem, no big deal. So this is our base case. In fact, we proved a whole bunch of base cases here because we weren't sure where we were going to start, and I'm really glad that I did because I made a mistake. So let's go to the inductive hypothesis. The inductive hypothesis, assume any amount greater than or equal to, let's say 8, any amount greater than or equal to 8 is possible, up to and including some fixed value k. Just like we did in the previous example, we are going to assume we can do it up to and including some value k. And what I mean by this is any value between 8 and k is obtainable using 3 and 5 cent postage stamps. So now for the inductive step, let's consider k plus 1. Now, we talked about modular arithmetic a little bit before the spring break. We talked about divisibility with respect to a given number. I don't remember what we used as the notation, but divisibility with respect to a given number d, say. And we saw that when you divide a number, when you divide one natural number by a number d, one of d possibilities was possible. So when you divide by 2, for instance, there are 2 possibilities. You have a remainder of 0 or a remainder of 1. When you divide by 3, there are 3 possibilities. You have a remainder of 0, of 1, or of 2. More generally, when you divide by d, you have d possibilities, a remainder of 0, 1, 2, etc., up to d minus 1. So anytime you're dividing by a certain number d, you end up with one of those remainders from 0 to d minus 1. We're going to consider dividing by 3 since that's our smallest denomination here. So there are 3 cases. If let me put it this way. Case 1. If I'm trying to think, there might be an easier way to say this rather than looking explicitly at the remainders. Let's consider it this way instead. Consider k plus 1, and let's examine or look at k plus 1 minus 3. So we might as well assume that k plus 1 is greater than or equal to 11 because we've already proven these cases here. So k plus 1 minus 3 is equal to k minus 2. And now let's consider cases. Case 1. If k minus 2 I'm rethinking the way I want to prove this again. I'm rethinking this again. I'm trying to think of what the least onerous way to do this is. And I think it may be as I was originally considering looking at remainders. So consider k plus 1. And what's going to happen is we're ultimately going to go back to one of these 3 cases here. Case 1, if 3 divides k plus 1, if 3 divides k plus 1, we are essentially in the case, it's kind of like the 9-cent case here, because 9 is, as we see, 3 times 3. 9 is divisible by 3, and so we are essentially an even multiple of 3's away from 9 cents. If 3 divides k plus 1, then k plus 1 is equal to 3m for some m. So we use m 3-cent stamps. So in that case, we can do it in just directly by using m 3-cent stamps. For case 2, k plus 1 has a remainder of 1 when dividing by 3. And in this case, we are essentially in the case of 10, because 10 also has a remainder of 1 when divisible by 3. So what we can do is we can reduce the case of 10 cents. Then, k plus 1 minus 10, which is k minus 9, is divisible by 3. So k minus 9 is equal to 3m for some m. And in that case, we have 3m to make up k minus 9, and then 10, oh my goodness, where do I want to put this? I'll put this up here. So I'm running our room down there. This is case 2 continued. So we're reducing to 10 because we recognize that 10 and k plus 1 both have the property that they have a remainder of 1. And that means that k minus 9, which was k plus 1 minus 10, is 3m for some m. But 10 is made up of 2 5-cent stamps. So finally, k plus 1, which is after all 3m plus 10, is made up of m 3-cent stamps and 2 5-cent stamps. So we can make up k plus 1 in that case as well. Going back to a second base case. And then finally, case 3, if k plus 1 has remainder 2 when dividing by 3, we can reduce to the 8-cent case essentially. K plus 1 minus 8 is k minus 7. We'll have no remainder and will equal 3m. And thus, k plus 1 will equal m 3-cent stamps and 8, which can be made up of an additional 3-cent stamp and a 5-cent stamp. So what we really need is m plus 1 3-cent stamps and 1 5-cent stamp. And that will do it. So in this case, rather than going back to multiple inductive hypotheses, here we are in the inductive hypothesis, we went back to multiple base cases. We reduced our inductive step to multiple base cases depending on what remainder we saw when we divided by 3. So sometimes multiple base cases will help you out in strong induction, and sometimes the stronger inductive hypothesis will work. There are other ways to approach this proof where we would consider multiple inductive hypotheses, much as we did in the previous proof, but I chose to go back to multiple base cases here. And again, I was really happy that I made that slip regarding the original statement of the proof, because I think it's important to show that you can just adapt. This was a question that came up by email last week at some point. You can just adapt your statement. If it turns out not to be true for a particular base case, well, just change your statement. In this case, I was thinking, well, we can do it for 7, but no, you can't do it for 7. We had to adjust. And the reason, by the way, I had to start at 8 rather than the modified statement of the proof started at 8 was because that was the smallest example from which we could proceed without any errors. So I hope this helps. I hope these videos are helping you to approach the reading and get some better grasp on the reading. Again, sections 5.1, 2, and 3, quizzes and problem sets are due next Friday, April 3rd. Sections 5.4, 5.5, 5.6 will be due April 10th. And again, I'll have the videos up a week prior to the due dates for any of the quizzes or problem sets. And please don't forget, you all owe me 2 total, whether in person before the break or now by video. You owe me 2 problem submissions. And I will very soon post exam number 2, which will deal with chapters 4 and 5. So thank you for watching. I'll catch you all again soon, hopefully dressed a little more appropriately.